Okay, so today's subject is spectrophotometric curves and their interpretation. Those are, when we've talked before, those are our object curves. This is not in your book anywhere. Most of it's in your handout. We have our spectral curves. It's hard to say after a while. What do we use those for? One of the first major uses of spectral curves is obtaining raw data for tri-stimulus values and LAB numbers. This is what we've seen before. We take our spectral curve, which is our middle curve here. We multiply it by our standard observer and by our light source, and we can calculate X, Y, and Z values, and from that we can calculate LAB numbers and LCH numbers and CMC numbers and all these other numbers that you'll get a chance to calculate in the weeks to come. So that's one use of our curves. Another is for input for automated color matching systems. When somebody goes to work as a color matcher, you can match colors several different ways. One of them is visually. You just look at and decide which colorants you think you should put into it, mix those up, make a sample, look at the two visually, and then decide if you need to adjust it. Another way you can do that is to have your spectrophotometer and a computer do that. There's color software that is designed so that you measure your sample on the computer, measure it with a spectrophotometer, that data goes to the computer, you have a bunch of colorants in your database. It tells you what is in it, what pigments are in it, what colorants, and how much of each one. And theoretically, you go weigh that up, and then you get a match. Practically, it doesn't always work that well. Sometimes it works good, sometimes it works horribly. You still have to know what you're doing to do that. What you do when you set up these programs is you have to put a lot of work into it up front. For every colorant you have to make up mass tones. White letdowns are the colorant plus white, basically, and you put it in the resin. The mass tones are just the colorant itself, and the black letdowns are colorant plus black plus resin. It may be anywhere between 5 different samples up to 10 or 12 samples for each colorant that you have in your system, in your palette. And then you have to read all those into the system. Some of them you just read in reflectance, some of them you read in transmission and reflectance, depending on whether they match opacity also or just the color. You know, you figure you have to make up 10 batches, say, for every single colorant you have. Make sure you make those batches right, because if you make mistakes when you make up these samples, then you read them into the computer, then the data is wrong and you screw up your system. But that's another use for these curves. The computer calculates K and S values from the samples, and you're all wondering, well, what are K and S values? You'd like to know what that equation is, because you always like equations, and that's what K and S values are. And later on in the term, we'll use this equation to make some determinations about pigments and strengths and things like that. It's really not that difficult to do, because there's a table that goes along with it. But the computer does this, calculates these K and S values, which are important for these color matching programs. The R is reflectance from our spectral curves. K is called the coefficient of absorption. S is coefficient of scattering. This little symbol there is wavelength. This equation is good only at a specific wavelength. So to do these calculations, you have to do a whole lot of calculations. These are things that are done by a computer. You never do them by hand. We can also use spectral curves as fingerprints for colorants. We can use them for direct and comparative interpretation. If you understand how curves work and what they mean, you can look at a curve and determine what pigments are in that particular combination, and that's when we'll actually do an exercise where we'll get to do that. Or you can get an idea what the color is by looking at the curve. Okay, here's an example of an actual curve, And this particular pigment is phthalocyanine blue, which is a very common, the most common blue organic pigment that's used in industry. This particular shape is very specific to this pigment, and especially over on this side here. That little hump on the end tells us that that's a phthalo blue. The two different, there's actually two curves there, and the differences in this area here on the right, the RS stands for red shade, and the GS stands for green shade. When we talk about colors and colorants, we say it's a certain hue. It's red, it's green, it's blue. But there's also something called the undertone to it, which is secondary color to it. We talked a little bit about the LAB system, not too much, but in that we have the red-green scale, our blue-yellow scale. In this case, we have a blue, so blue would be in this direction. We have the difference between them. One of them is a red shade, and one of them is a green shade. If you looked at the two of them, you could see a difference. One would look redder, and one would look greener. They'd both be blue, but there's a difference there. This undertone or shade of pigments are important when we're doing color matching. Even without looking at, say we had two chips with these two colorants on it, we could tell by looking at the curves which one was the red shade and which one was the yellow shade, just by the shape and where this part of the curve goes up. You'll see that that's important as we go through this a lot. Here's another pigment. This is methylene violet, and this happens to show two different white letdowns. The numbers there, this is 98% white, 2% colorant, and the dotted line one, or 92% white, 8%. The dotted line is stronger, and we can tell, you'll see a little later on about different things from the curve. The shape of this curve is the same whether it's lighter or darker. That's the only difference, and that shape can tell you what the pigment is, what the colorant is, and that's what's important. When you look at curves, it tells you what the colorant is, and you can use it as a finger point. Here's another one, red 2B. A red is relatively flat in this part of the spectrum, and then it goes up very quickly. We call that the inflection point, and what wavelength that happens at is important for determining what the color is that we see. There's different types of spectral curves. There's actual curves for illuminance that we don't generally use too much in industry. Doesn't really mean too much to us. For dyes, there's curves that are called transmission curves. So what the unit does, it measures the light that passes through the sample. And for pigments, inks, and paints, we measure reflection curves that measures the light that reflects off of the samples. So that's the difference. One of the problems with plastics is that many of them, even if they're colored, are translucent, which means there's some light that passes through it and there's light that reflects off of it. So, if you use just a reflectance curve, you don't see that transmission part, and vice versa. But there are two different curves that we can look at. When we talk about these curves, mainly from now on we'll be talking about reflectance curves. But really the same points are true for the transmission curves as they are for the reflectance curves. We can use these spectral curves to do several things. We can measure reflectance and measure transmittance. That's essentially what they do. We can look at the absorption peaks, see where they are to help us determine what the colors are, and we can compare two similar curves to see what the differences are in the formulas that make up those samples. They can show what the hue of a color is. They can show what the tint strength of it is. That's one of important use of them. They can show lightness, can show chroma, and whether it's clean or dirty color. And what we mean by clean and dirty is a clean color is a nice, bright, chromatic color. A dirty color is something that's more closer to gray, less chromatic, not as bright. They can also be used to calculate colorimetric data, tristimulus data, and identify color types, chemical types. If you have a certain colorant of a certain chemical makeup, it'll have a characteristic shape to its curve. So the shape is what's important. And we can use them to identify metamerism. If the shape of the curves are the same, you won't have metamerism. If there's a difference in the shape, then that's what causes metamerism. Well, that's how you can see metamerism anyway. So spectral curves can be made up for individual colorants as well as mixtures. When individual colorants are used or individual colorants are investigated, they are made into tints. We mentioned that a little earlier. When we want to look at the strength of a particular colorant, we make a tint. You can't really tell strength by looking at a mass tone, which is just the colorant themselves. We make tints up in very specific concentrations. Generally speaking, if we're doing an organic colorant, we'll do 95.5, 95% white, 5% colorant. Inorganic will be 90% white, 10% colorant because it's not quite as strong. TiO2, does anybody know what TiO2 is? You chemistry experts. What's TiO2 stand for? Titanium dioxide. Yep. And that's the most common pigment in industry, and it's a white pigment, and it's used just in tons and tons in the industry. Mix our colorant with the TiO2, and we can get an idea of what it looks like in tint, how strong it is. I have some curves here that show some theoretical colorants that would be great if we had. They're not real. It kind of gives you an idea of what causes certain things in colors. So no color has a real sharp rise like these do. And of course, just like all the rest of us, real colorants, just like real people, aren't perfect. Perfect colorant would be it absorbs light in all the wavelengths except for one very specific wavelength, and then it reflects that perfectly, and gives you that very pure color. Unfortunately, nothing like that works, or no pigments like that work. Here's another example where it absorbs all of these wavelengths and reflects all of those wavelengths perfectly. And again, we don't see that for sure, but it kind of gives you an idea of what it would be best if we could kind of design a pigment the way we wanted it. So the important parts of the curve, when we look at it, there are several things that we need to consider. The absorption peaks, and when we talk about peaks, it's kind of a, I don't know, maybe a misnomer compared to what we think of in peaks if we talk about mountains. If we have a sample that looks like that, or a curve that looks like that, kind of the phthalo blue curve, the absorption peak is actually the valley part here, you might consider. It's the lowest part on the curve. That's considered the absorption peak. That's where the colorant absorbs the most light. Because when we're analyzing curves and want to see what part of the curve makes it into a mixture, or where it absorbs light, not where it reflects it, is the important part. Because if you consider what's going on, if you have a pigment is in a mixture and it's absorbing the light, it's not available to reflect, takes it away, it subtracts it from the possible colors that are available. Useful when comparing two similar curves, as in QC procedures. If we have a standard and a sample, we can see how far off they are and where they're off. Strength differences can be calculated from the difference in the absorption peaks. So we could actually have another curve that would be like this. This difference, later in the course, will show you how you can actually calculate, using those curves, what the strength difference is between those two particular colorants. We'll look at some examples here. Colorant represented by curve 2 has a lower absorption peak than that of curve 1. Therefore, curve 2 indicates a stronger colorant. And these are, again, just made up curves, but you can see this curve, curve 2, goes much lower than curve 1 does. So because of that, these absorption peaks are much lower. That's a stronger pigment. If these were two white letdowns with the same concentration, same amount of white, this pigment would be stronger than that pigment would be. It also would be darker than this one. The higher up the curve is, the lighter the particular colorant is. And this is a curve of an actual pigment. But this is our violet. And what we have here are two different white letdowns, like I showed before. The lower one has a greater percentage of colorant in it than the higher one is, so we can see that it's lower on the graph. Even if it didn't say which one was which, it would be easy to tell that this one is the 8% colorant and this one is the 2% colorant. This is a red 2B barium pigment, very common, inexpensive pigment. You can see that as we go up, we have more reflected light, 2%, than we do in the 13%. So the 13% is the strongest, which makes sense, and the darkest. To look at this particular pigment, this is the blue side of the curve, and this is the red side. There's not much difference in the red here, really. But on the blue side, you can see there's a big difference in how much light is reflected. Because it has a hump over here on the blue side, that means when we were talking about reds, this would be a blue shade red. And notice what happens as we add white to a sample is that not only does it get lighter, but it becomes bluer. So if you're in a color matching application and say you made up a sample and it's the right shade of red, right amount of blue in it, but it's too dark, you might think, well, I'll just add white to it and I'll keep the same shade and it'll just get lighter. But what would happen in this case is that by adding white, you'd actually make your color bluer. So it changes the hue also. So those are the kind of interactions you need to consider when you are making adjustments in a color match, just to make it more interesting and more complicated. Another thing to consider, the overall height of the curve determines the chroma or the purity. We've talked about chroma already in other classes. And this is defined as the span of the curve from the top of the highest peak, reflection peak, to the bottom of the lowest absorption peak. So from the highest point on the curve to the lowest point. The larger the span, the more chromatic the color. The color represented by curve 2 has a larger span from the top of its reflection peak to the bottom of its absorption peak than that of curve 1. Therefore, curve 2 indicates a more chromatic colorant. Curve 2 has a big difference between the lowest and the highest point, a bigger difference than curve 1. Curve 2, or it represents a more chromatic color because of the difference between the top and the bottom. And again, you can tell that by looking at the samples, but you can also tell it by looking at the curves and not even seeing the sample. These curves can help you get a lot of information about your colors without even having to look at them visually. Okay, let's look at some real pigments here and look at the difference in chroma between a couple pigments. This is phthalo blue, which we've looked at before, and we can see there's a very large difference from the lowest part of the curve to the highest part of the curve. And if we compare it to Midori blue, which is a blue pigment also, but an inorganic blue pigment, which is much less chromatic, we see that there's a much smaller difference from the lowest part of the curve to the highest part of the curve. So that gives us a much less chromatic pigment. You can tell that by looking at the curve. We're not having to look at the actual chips. We could tell it from either way. Another key aspect of a spectral curve is the position of the reflection peaks and or the inflection points. These positions determine the hue or the shade of the color. So if we look where the curve goes up quickly and then follow down from that point to the scale that shows the wavelengths of light that correspond to it, where we can determine the hue of that particular color. The wavelength, if you think back to one of the earlier classes, that corresponds to the curve is the hue of that particular color. Here's a picture that shows that, and we can see The inflection point starts at about 490 nanometers and goes straight up from that, from about 10% reflectance all the way up to about 80%. That steep rise, that place on the curve where it changes direction, is the inflection point, and where that happens determines the hue of this particular colorant. Looking at a real pigment, a red 2B again, we can see that there's two lines there, and the difference between those two lines is the shade of the color, or the undertone of the color. Both these pigments are red, but one is a yellow shade and one is a blue shade. The curves themselves look pretty much the same as far as the shape goes. There's a little difference, but mainly it's the same. The difference is the wavelength where that inflection place takes place. The one on the left is our yellow shade. It occurs at a lower wavelength. The one on the right is the blue shade, and that inflection point takes place at a higher wavelength. Seeing where that point is, we can determine the hue of the color. Chrome yellow, another pigment that has two different shades associated with it. We have primrose chrome yellow and medium chrome yellow. And again, the shape of the curves are very similar, but the position of the inflection point is shifted slightly to the right for the medium chrome than it is for the primrose chrome. It gives us a different undertone, or a different shade. Again, they're both yellows, but one is a little bit different yellow than the other one. Our phthalo blue shows that in this particular case, steep rises is in the blue end of the spectrum, and that means that we have a color that's a blue. And again, this is a very chromatic and strong blue pigment. And we have two types, the red shade blue and the green shade blue. And all of the curve that causes either a red shade or a green shade happens on the right side of the curve. The actual blue side of it stays pretty much the same. The red shade has a peak in the red area of the curve. The green shade does not. Here is another phthalocyanine pigment. It's phthalocyanine green, and it has a very similar shape to the phthalocyanine blue pigment, except that the big peak is shifted over to about, the middle of the peak is about 500 nanometers, which makes it a green instead of a blue. Now, as we had with the phthalocyanine blue pigment, we have a very distinctive shape to it on the right hand side of the curve. It's a little bit different than the phthalo blue, but it's distinctive nonetheless. So when you have this shape with the little dip and then goes back up, this tells you that you have a phthalo green pigment in your mixture, or in your color.